So it's a pleasure to be here. Thank you for giving me the opportunity to talk, and kind of strange to be speaking across all these different time zones. So here it's 8 in the morning, and oddly enough, it snowed last night all of a sudden after hitting 80 degrees a few days ago. So it's sunny, but a bit of snow on the trees. Anyway, so what I want to talk about today is a little bit of the work that I've been doing on geometry and control of quantum systems, sort of mainly systems connected to the environment in some way or another. So what I want to discuss really is some ideas about how one controls quantum systems. Of course, there's been a lot of work over the years of this. I want to discuss something about how we've incorporated damping. And again, of course, as many of you know, there are many ways to do this, but in this particular case, I mainly want to look at Lindblad dissipation, but I'll discuss a couple of other things. And then I'll discuss a couple of control problems, in particular the control of purity, which I worked on with a student of mine called Patrick Rooney in Rangan, who's at the University of Windsor, not so far from here. And if I have time, I'll say a little bit about optimal control and spin oscillator systems. So just to give a little background, first, just about controllability. So the basic control system is you're given a system usually called the drift system, which describes the dynamics without the control. In the linear case, it's something like x dot equals ax. More generally, it can be any reasonable nonlinear system, x dot equals f of x, and then one has a bunch of controls. And again, in the linear system case, if the system is, say, n-dimensional, you have a matrix B, which is n by m, and m less than n controls, which makes it interesting. So the basic theory of controllability was developed for linear systems back in the 60s. And for a system to be controllable, in other words, to be able to drive it from one point to another, there's a basic rank condition on the matrices involved. And this is the famous Kalman rank condition, which I've written here. Quantum systems generally are bilinear. So one has a drift system, which is the uncontrolled, basically Hamiltonian of the system. And then one has various input Hamiltonians as well. And the system controls are often, for example, lasers, and they enter into a bilinear system as multiplicative controls, UI, of the system Hamiltonians. So the system does tend to look like the system I've written here, this affine nonlinear system, x dot equals f of x plus sigma ui gi of x. And one can generalize this still further to have the controls entering nonlinearly. And there are various, so the controllability for such a system turns out to be quite complicated. In general, it's an NP-complete problem. But the basic sort of necessary condition is, again, a kind of rank condition, which in this case is the Lie algebra rank condition. That's the smallest Lie algebra containing the drift vector field and the various control vector fields should basically span the Lie algebra or the tangent space to the manifold you're on at any point. So I'll come back to that. So let me say a little bit now about damping. So the inspiration actually sort of goes back to some work that I did with Michael Weinstein and Patrick Haggerty a long time ago on radiation damping. So we were interested basically in stability. And this goes back to work that I did with Jerry Marsden and others on using energy momentum methods for stability, and other people like Daryl, who's here, were involved in this. And we were interested in what happens when you add damping to the system. For example, if a system was shown to be unstable using the operative function given by the combination of energy and momentum, did the system really become unstable? And so in that case, you can add a kind of dissipation, which makes the system non-Hamiltonian. But we were interested in what happens in the Hamiltonian setting. And one way to do that is to model the damping by radiation. So you connect the system to a bath, as one does in quantum mechanics. And so we looked back at a number of things. In particular, there's this famous Lamb model, which goes back to the early 1900s. And it was actually an early model for quantum mechanics. In fact, you have an oscillator coupled to a string. So this is the simplest model one can possibly imagine for a system connected to a heat bath. And the idea is that the vibrations of the oscillator transmit waves into the string and are carried off to infinity. And thus the oscillator loses energy and is effectively damped by the string, but the system remains Hamiltonian. So this is the basic Lamb model, and in a little more detail. So if you model the displacement of the string by W, you have a mass density rho and a tension T. You connect it at the point x equals 0 to an oscillator of mass m. And you have a system that sort of looks like this. So you have this oscillator at one point, there's the string that carries off the oscillations, and you have this wave equation, WTT equals c squared WXX, and this is connected at the point 0 to an oscillator through a term with a multiplicative constant t. And in this case, the connection is Wx at x equal to 0 is this expression here, a jump discontinuity of the slope of the string. So this is an infinite dimensional Hamiltonian system. That's the oscillator connected to a wave equation. And you can solve for W and reduce. That's the rather beautiful thing. So what you can check is you can just basically use a little bit of Laplacian analysis, Laplace transform, and you can show that you get a reduced form of the dynamics describing the explicit motion of the oscillator subsystem, and the coupling term just reduces basically to Rayleigh dissipation. So you have the basic harmonic oscillator, and you have this extra term 2t over c times q dot, and that's just a damped harmonic oscillator, and you can look at stability or anything else in this setting. So this is sort of a nice way of thinking about a system connected to a bath in a simple setting, and it's related to a whole lot of course, many more sophisticated approaches that were used to model a system connected to a bath. And it goes back to work of Feynman and Vernon, Caldera and Leggett, and more recently, of course, there have been many things. Some interesting recent work was on quantum circuits by Jürgen Denker and Gao and Yang. It's also related to certain stochastic approaches. I'll just make a remark in a second about that. And of course, there's the famous Lindblad dissipation and many other things. So that was sort of some of the inspiration just for looking originally at some of these damped or control systems or systems connected to a bath. So as far as the quantum side of things is considered, so we've looked at a number of things. So my work on this really began by looking at a paradigm for quantum computing. So there were a number of people here and other places, Stanford and Maryland, looking at quantum computing. And of course, there are different ways of looking at a quantum computer. The particular system people were interested in looking at here was a crystal of trapped ions. So basically, again, this is a system that's connected in this case to a harmonic oscillator, but it's a two-level atom, a qubit, coupled to a quantum oscillator, or a harmonic oscillator rather, and it's an example of a quantum system with an infinitely large number of accessible states. And of course, it's motivated by producing quantum computers and being able to produce entangled states of qubits. And again, there are varying degrees of sophistication and different types of ways that people model these systems. So here is a picture of this work. This was the lab of Chris Monroe, who was here at the time. Now he's at Maryland, but these are basically two ions in a bath. These are basically Rydberg atoms. So you see two of them connected together. And the idea is you should think of them as a couple of spins connected in some way. And you sort of model this sort of connection by oscillations, which you model by a harmonic oscillator. And so here's another little picture of that, and here's another one that goes up to about five atoms. And I believe in recent work, people have been able to push that up to even 11 or 12 of these atoms. Of course, it's still a complicated system, and you run into all these problems of trying to preserve the entanglement and prevent phase decoherence and dissipation from occurring. So the goal really for a system like this, and this relates to what we think about it, is to sort of think of it as a basis for a quantum computer. You're trying to derive the system from one quantum state to another, but at the same time preserve the quantum features such as entanglement. So a little more detail. So this trapped ion qubit formed by two hyperfine states of a laser coolable ion separated by a certain frequency. The qubits are coupled by the vibrational modes of the ion's motion. And basically, as I said, what you're looking at is trying to control the system. And the way you do that is basically by a pair of optical beams. So in this case, you have a quantum system which you're addressing by a pair of optical beams. So you have two controls for this coupled sort of harmonic oscillator spin system. And of course, again, there's been a lot of work on this, and I'm sure many of you are more expert on some of this than I am. But anyway, so there are many exciting ideas related to the control of these systems. Famous work is that of Eberle, Law, and Clear. And in some work with Chicha Rangan and Roger Brockett, we looked at how to control these distinct systems, sort of based on this work of Eberle and Law. And the idea was to sort of translate these basic control ideas of controllability and so on to this setting. So if I have time at the end, I'll return to that. But I'm going to mainly talk here about steering the system in terms in the presence of Lindblad dissipation, and we'll be modeling the dissipation in this case by these Lindblad terms. And so the systems that we're looking at are mainly going to be finite dimensional. And one of the interesting things about this is, so of course the given system here is an infinite dimensional system. It's a spin system connected to a heat bath, or in this case, this infinite system, which is the harmonic oscillator. But in fact, one can truncate the system. So that's one of the interesting things that was done experimentally. So you can turn off specific transitions to truncate the Hilbert space. So you can actually make the system finite dimensional practically in the lab, even if there is something like an infinite dimensional system like a harmonic oscillator. And the idea is then you can address the system using finite dimensional models. So we've used sort of both of those approaches. You can approach it either from a finite dimensional view or the infinite dimensional setting. But here, basically, I'm mainly going to stick to finite dimensional. And so this is what we sort of generally call flag-based control, and I'll try and explain why we call it that. So again, this is the idea of controlling systems for various purposes, coherent control of chemical reactions or quantum computations. And the idea is you want to counteract the influence of the environment, which causes decoherence and dissipation. And again, of course, there's a large literature on that. And again, it's very it's complicated to model the environment. The simplest case, of course, is if you have a Markovian sort of time-independent environmental system, then you can use the Lindblad master equation. And there's been a lot of work sort of on this, some work by Gao and Mark James and others. And basically the idea is you control the basic system. There's a Lindblad term which affects the dynamics. And the control functions affect the system Hamiltonian, but block the Lindblad terms. But there has also been some work, and we just started looking at this a bit recently, where you actually control the open system dynamics as well. So basically, the idea is you're controlling the system on a unitary orbit. That's the sort of Hamiltonian dynamics, and then there are these perturbative terms. And the idea is basically, if you don't have the Lindblad terms, then the system is on an orbit, right? So even if you have a sort of Hamiltonian with controls, you're basically on the orbit of the Hamiltonian, which could be time dependent. And the idea is if you have the Lindblad terms, it can take you off the orbit. And so one of the interesting things about this is one often thinks of the dissipation decoherence as hurting one, which in some sense it does. But for controllability, sometimes it can be helpful. And a particular example is controlling purity, for example. So if you're, and I'll come back, this is going to be my main example in a way, if you're at the interior of the Bloch ball, for example, and you want to get to the edge, then the Lindblad term is something that helps you because it enables you to escape basically from these adjoint orbits. So in particular, you can change the purity of the system, trace rho squared, rho being the density operator, which is constant on any orbit. And that's basically the idea I'm going to look here. And so we're going to look basically at the interplay between being on an orbit in a Hamiltonian setting and how you kind of use the controls, which are also Hamiltonian, plus the Lindblad terms to move around. So basically, so if you take the n=2 system, which again will be my main example, you can turn the sort of inter and intra orbit dynamics into a control equation. You can treat the orbit itself basically as a kind of state variable. And the position in the orbit is a flag, which it comes from the action, say, of a group. In this case, the unitary group on the Hilbert space. And there's the nesting of subspaces. And basically, the idea is to move along this flag using a combination of the controls and the dissipative terms. And so of course, it's a nonlinear system in this case. The orbit's it's a manifold. And you can do a certain amount of this analytically, and particularly in the n=2 case, which I can show you. But as you get to higher dimensions, it becomes more complicated, and you can sort of use a mix of kind of analytic and numerical terms. And the idea is, so basically the control problem that we're going to look at here, you can look at various things. You can think about how to move around in general in this flag space, if you like. But the idea is, in this case, is we want to try and move from, say, a completely mixed state to a pure state. That'll be the sort of main goal. And what we're going to show basically is you can say in the two-dimensional case, you can find a thread through the space, which is called the Bloch ball, which sort of minimizes locally the time derivative of trace rho squared. So basically, you're trying to minimize or maximize the purity as you move. So the idea is to try and find some control that moves you around in some direction, either increasing or decreasing the purity. And so you can turn it into a kind of maximization problem or even an optimal control problem. Okay, so to go to the basic setting here, so we have this open quantum system. It's described by a density operator. If the dissipation is Markovian and time independent, the density operator obeys the Lindblad equation. And you have an equation that looks like this equation here, d rho dt, the Hamiltonian term plus the Lindblad term, and the Lindblad term, this is the one I've written here, which is pretty general. It's a bit more general than we use, but this is the basic idea. So the braces here are the anti-commutator. H of t is the Hamiltonian, and Lm, these capital L's, are the Lindblad operators. So you can also think of it, so you, of course, you know, everything I'm going to do here is basically deterministic, but you can also think of it a little bit in the stochastic setting if you want. So it's certainly related to that. So, so if you're looking at the stochastic setting, you'd consider an Ito term with sort of the Hamiltonian piece plus a function f which ensures the flow lies on the orbit. And basically you choose the terms to make sure that the system lies on the orbit, and in particular the trace of rho squared is preserved. And basically if you take rho dot rho using sort of basically the Ito calculus, and you choose it so that things lie on the orbit, that means rho dot rho is equal to constants. You get an Ito equation, which looks like the equation I wrote at the bottom of the page here, 1.5. And you can check that again, you get some sort of double bracket term, omega I, omega j, comma rho, the kind of Lindblad term, which preserves the dynamics. So it's in some sense, it's related to the stochastic setting and also to the infinite setting, but we're just using the simple deterministic form of the Lindblad term. So so you can do this quite generally, and if I have time, I'll show you the general case, but it's kind of nice just to look at the n=2 case, which has a lot of the nice features of the general setting, and you can do very specific analysis. So in this case, you can think of the density operator rho as identified with the Bloch vector n in the ball. And this is the identification, this equation 1.7. So rho is equal to 1/2 times the identity matrix plus the sum over Pauli matrices. And in this case, the Lindblad equation reduces to this equation here, 1.8 for n. And so there's a sort of constant affine term, a cross product, h cross n. So it looks a little bit like rigid body dynamics or something like that. And then you have a dissipative term. And here, so H basically represents the traceless parts of the Hamiltonian, and Lm represents the sort of the operators, the Pauli operators, at least the Lindblad operators expressed in the basis of the Pauli matrices. So the Pauli matrices here are giving you this sort of Lindblad form.
Excuse me, what's A?
So A, let's see, so here it is. So these are the system parameters. So let me just show you. So that's the equation, and this is what they look like specifically. So A is a sum over these operators, L, which represent the Lindblad terms, and similarly for B. So that's how the Lindblad terms come into the equation. And you can see that A is a positive semi-definite matrices, a semi-definite matrix. So its eigenvalues are non-negative. And additionally, there's an inequality that the vector B applies, which turns out to be useful for analyzing the controllability. So so again, yeah, so this is rho expressed in terms of sigma. This is the equation. And so the Hamiltonian again, H is expressed in terms of the sigma J's, and the A's and B's encapsulate the Lindblad terms. Is that okay? Okay, so the idea is, and I'll show you some pictures in a bit. So the idea is you want to think of this. So you want to think of this as sort of evolving in some sense on the Bloch ball. And as I said, the sort of problem we're going to look at here, although you can look at all sorts of problems, is the problem of sort of increasing the purity of the system. And that means essentially getting to the boundary of the Bloch ball. So the idea is you want to kind of use the system to sort of have a path through the Bloch ball. And so it's convenient both for, sort of intuitively and for the analysis to divide the system into its radial and transverse components. And basically you want to drive the system in the radial direction, but your controls are sort of Hamiltonian controls, which are in the transverse direction. So the whole game here really is you're controlling it along sort of, if you like, radii, along sort of orbits around the origin, if you like. That's where your control is, and you're using the sort of Lindblad pieces to break the symmetry, to drive you away from those orbits so you can move to the edge of the ball. So in any case, so what we do is we write n here is equal to Rn hat, and then you can break the equation up into two pieces, an equation for R and an equation for n hat. And the perpendicular subject, the perpendicular here indicates the component perpendicular to n. So you're basically breaking it up into radial and transverse pieces. And there are various sort of little bits of interesting things regarded to the analysis depending where you are in the ball, in particular at r equals 0. So r equals 0 is sort of interesting. So dn dt, if you look back at the equations, can be large for small r, but you can show that trajectories that pass through any, for trajectories that pass through n equals 0, it's well behaved. You can check that dn by dt is equal to b, and sort of just before or afterwards, n is just equal to b delta t. And therefore at the origins, you can check that the equations reduce to this nice form here, which and the equations are still nicely bounded. So even though you might think there's some weird behavior at the origin, things still behave quite nice. But you can also just start just a little way from the origin. So let me so I'll go through some of the analysis, but so let me give you the general idea though. So basically the idea is so in a control theoretic context, you're able to choose the Hamiltonian. The Hamiltonian only appears in the transverse equation, which is the equation 1.13. So let's just go back for a second. So that's that second equation over there. So there is H appearing in 1.13, but it is coupled to 1.12. And the goal is to use your control over H to control N and then control R. So that's the basic game here. So the Hamiltonian appears in the transverse equation, while the radial component has no explicit Hamiltonian dependence, and we want to be able to steer the transverse equation in order to influence the radial. And basically, we assume we have fast and complete controllability. So in the absence of Lindblad dissipation, you're able to steer between any two points on the orbit in a very short time, or at least a time much shorter than that associated with the Lindblad operators. and this is generally, it's a reasonable assumption. So basically, you can think of sort of lasers acting on the system, as I mentioned earlier, and you can, if they're unbounded, of course, you can move as fast as you want. So you can think of basically the system without the Lindblad equations as equations where you can move sort of instantaneously, if you like, virtually on these orbits. Okay, so the idea is what we're interested in doing is optimizing the function f as r varies. So we'd like to find an orbit, in other words, that optimizes the interorbit speed, right? So this is the main goal. And you can do it in a kind of static way using the method of Lagrange multipliers. And if you do that, you get a certain, you can use a Lagrange multiplier condition, you know, to sort of maximize the speed subject to the dynamics. And this leads to a kind of optimization problem and a 6-degree polynomial, which you have to solve. So I won't go through details. It's sort of possible, in fact, in this case, but it doesn't scale up nicely to higher dimensions, which you're interested in. So we're going to try a sort of different approach with better scalability. So it's easy to check, for example, if I look at f naught, again, that's the origin, that's b dot n. You can check that f naught is maximized, for example, at n plus equals b hat and n minus equals minus b hat, and 0 from any vector perpendicular to b. And basically the idea is you want to increase r from 0. So that's sort of the basic. So if you think of the origin, that's one way to maximize things. You want to move as fast as you can in the radial direction. But of course, there's dynamics. So the idea is actually to do the following. So as we increase r from 0, we exist whether they're differentiable functions n plus minus 1 of r with feedbacks m. So you think of this as a kind of feedback that you're putting into the system, such that n plus minus 1 of r is a local optimum for the functions fr for every r. So basically you try and optimize the speed as you sort of move outward through the ball. And if such functions exist, we call these differentiable curves maximizing and minimizing threads. So we're trying to maximize the speed as we sort of move outward, say from the interior of the Bloch ball. So we know that n lives on the sphere S2. A tangent space of S2 can be identified with a two-dimensional vector space, and you can compute the derivative fr at a point n with respect to a variation n, a variation epsilon rather, as I've written here. So basically what you're doing is you're computing the derivative of f along the orbit, and the idea is you want this thing to be 0 to maximize things, and you can check that again. You get some sort of nice expression for the critical points. And again, at the origin, you see that n hat is equal to plus minus b, and these are the only two critical points. But this is something we want to sort of analyze as we move outwards. So the idea is to vary n hat with r so that it remains a critical point of fr, right? So we want to make sure we're getting the maximum speed as we move outwards. So we differentiate df with respect to n as we move outward. And we have to take into account the fact that the tangent spaces at each n hat are different. And we also must vary, we must also choose the variation that it remains perpendicular to n hat. So that's the basic game. So we basically maximize our radial speed. So you can do this little computation using some, basically it's just calculus, but you get, in the end, you get a nice expression for what the derivative of r with respect to r of drf of n dot epsilon is equal to, and that's this expression 1.23 at the bottom here. And the idea is you want this thing to vanish for arbitrary epsilon perpendicular to n, and you can find a nice explicit solution for this just by projecting both sides onto n hat. And let me just show you what, so basically that's it. It's just a calculation to get the maximum value for f. And we can come up with this little proposition here. So if you consider a point r0, n0 hat that is critical, in the sense that df n dot epsilon vanishes, you define the set of quantities here. Then you can check there's an open set in 0, 1 cross S2. For which this expression 1.28 lambda is invertible, and you get this very nice expression for n hat here. This has a it's sort of a differential equation for this tangential direction, which has a unique solution on some interval r. And on every point, the solution satisfies this optimality condition. And so these conditions basically hold for all points on 0, 1 across S2. And there exists two threads, n plus minus 1 of r, that satisfy the ODE. In other words, give you this maximizing velocity, if you like, or direction for the radial motion, and also have the initial conditions that I mentioned earlier at the origin. So, so sometimes these conditions fail, these sort of invertibility conditions, but you can actually still deal with that. So I won't worry too much about that. But the idea is you now have a sort of feedback condition, m equals dn by dr, that ensures that a trajectory remains on a critical point as it moves inward or outward from the completely mixed orbit at the origin. And that's really what we wanted to do, but we want to translate that into the sort of quantum or Hamiltonian setting. So the control variable really is the Hamiltonian. That's where we have the lasers that can act. So what we need to do is recover an appropriate Hamiltonian from a given feedback. And you can do that. So you remember that we had this Hamiltonian, which gives rise to the equation in the first place. So that was h hat. And actually, you can actually find what that looks like. And what you can show is that the Hamiltonian with the given feedback looks like this expression 1.33 here. So this is the Hamiltonian that you can act on, and with the right feedback. And once you've applied this correct feedback, the system will sort of evolve in an optimal direction. So that's basically the idea in this two-dimensional setting. So the idea is you want to sort of find these optimal points of FR, and that'll move you along through the Bloch ball. And I'll just jump ahead for a second. So I just wanted to show you a picture. So this is, and I'll come back to this in a second. So this big picture here is the Bloch ball. And this is and if you start off at the center of the Bloch ball, there's a trajectory, a sort of optimizing trajectory, which can get you from the center of the Bloch ball to the edge. And that's what this line is. But in fact, you can also think a little bit more about where there's still where the system is still going to sort of is going to change the purity in a positive or negative direction. And that's represented by this little sphere here, which I've drawn inside the Bloch ball. So let me just come back to that. So in addition to finding the optimal points of FR, that's sort of the optimal trajectory, which maximizes or minimizes purity, it's also interesting to locate the zeros. So that's where the purity is no longer maximized or minimized. So basically it turns out that for B not equal to 0, there's a chimney region in the Bloch ball inside of which the purity rises. So F hat of NR is greater than 0, and outside of which is less than 0. And if you want R to increase, you've got to steer inside this region. And you can actually compute the wall of this chimney, actually. So there's kind of a nice computation for doing that, for finding where you're still going to be increasing the purity. And so basically, again, you compute FR with respect to R, and you find where that becomes equal to 0. So again, you can do this computation quite explicitly, and you can show that for a given R, there is a continuum of zeros of FR, at least until the chimney terminates. And basically, you can move the system anywhere inside that chimney, at least you can steer it anywhere inside that chimney, and the purity is still going to be increasing. So, and so it's actually sort of possible to compute this, and there's actually an analytic solution. And basically, this is what you get. So if you carry out the computation, you get this rather nice expression for this ellipsoid, where the purity is still going to be increasing. So in general, however, the ellipsoid center and these axes are not aligned with the axes of A. But the intersection of the ellipsoid, with concentric spheres, which we're actually interested in, is not quite clean and analytic, but nonetheless, you can compute it, and that's what we were able to do. And so I won't go through the details of the computation, but it's possible to compute quite nicely using a sort of Rangan method for Lie groups, where this this chimney exists and where you get the maximizing and minimizing threads. So so this is basically the picture. So these are the optimizing threads and the chimneys for certain values of A and B, which remember represents the Lindblad term. So basically the picture here is inside the chimney. The dynamics drives the Bloch vector outwards, where the Bloch vectors outside have negative radial velocity, and this thread represents the optimal radial velocity. So this is sort of the general picture for the Bloch ball. Okay, so yeah, so that's just a little bit more about that. So I guess in the remaining time, I want to say something about the general case. So I have about, do I have about 10 minutes now, or it's
You have about 6 minutes,
6
plus
minutes,
5 minutes for questions.
Right. Okay. So I'm not going to go through all the details of the general case, but it's very similar. But it's kind of useful in a way to think about the general case, because it breaks down rather beautifully in a similar sort of setting. So the n-dimensional setting, again, we want to do the same kind of thing. We want to have a separation of the spectral and the flag dynamics. So you can think of again in the general setting, I have a density operator rho, which can be written as here in equation 1.39. So basically I have a state, so in the general setting, I have an n-dimensional open quantum system. It's described by a density operator rho on the n-dimensional Hilbert space. And it can be written in terms of its eigenvalues and orthogonal projections onto the corresponding eigenspaces. So rho is sigma lambda k pi k. And again, you want to think of the same kind of picture, that you're on some sort of unitary orbit which you can control, which is defined by the lambdas, but you'd like to also be able to use the Lindblad terms to move around and change the lambdas, basically. So, so the properties here of rho, all the eigenvalues lie on the interval 0, 1, and sigma lambda j is equal to 1. So again, so now we're going to look again at the general setting. We have Lindblad dissipation described by the Hamiltonian H, a set of Lindblad operators. And now we're going to think of this again as an n-dimensional system. Again, of course, it is possible to think of the infinite setting. And we're interested in controlling and investigating how a system moves between unitary orbits. So this, I think, is just helpful for understanding the geometry of what we just did very explicitly. So in the absence of Lindblad dissipation, the solution is just a unitary evolution, right? It's a quantum mechanical system. Rho is just equal to u of t, rho 0, u of t dagger. And u of t is a trajectory on the unitary group, satisfying u dot equals ih times u. And the eigenvalues of rho are invariant, right? So that sort of corresponds basically to moving on concentric spheres for the Bloch ball. And so so if you just look at the unitary orbit, u rho dagger, we basically don't leave the orbit, right? So we're just on this orbit, and without the dissipation term, we're stuck on the orbit. And the idea is we want to add Lindblad terms so we can get out of that orbit. And again, as in the two-dimensional case, we can assume fast controllability of the orbit. And the basic Hamiltonian in the general setting looks like this. So I have a drift Hamiltonian H naught, and I have a bunch of control Hamiltonians HI with control with terms UI of t. And again, basically you can think of those as lasers. And so for the atomic system that I showed you earlier, they're sort of basically red and blue sidebands for a laser. So normally you have two controls. And the basic problem often in control theory is just to check when the system is controllable. And generically, if you have a reasonable system, two controls turns out to be enough. In any case, so the unboundedness is a key property. So that means you can move fast. So and you think, so L of t is a bounded super operator. You can think of motion along the unitary orbit as being made arbitrarily faster than motion between the orbits. And I can sort of basically move instantaneously along an orbit and the idea is to use the Lindblad term to move me between orbits. And the idea, again, is this controllability condition that I mentioned earlier, you want the HI to span the Lie algebra so that any point on the orbit is reachable from any other. So you assume that you can move from one point of the orbit to any other point, and you can move in that sort of arbitrarily fast. And then you have this bounded kind of Lindblad dynamics, and the idea is to think about the control. And you can sort of generalize what I did in a kind of nice way to this setting. So now you want to write down a linear ODE for the eigenvalues and also something for the projectors, basically. And it turns out to have rather nice geometry associated with it, which I'll just mention in the last couple of minutes here. So if you let lambda be the vector of eigenvalues written in increasing order, you let pi be the interval of corresponding projectors, you can check that lambda lives on an n simplex with vertices 1, 0, 0, and so on. And there's some choice that you can make here, but basically you're on a simplex, which is also a nice geometrical object. And you can check that, so the simplex is an n-1 dimensional subject of Rn, which you can project onto Rn minus 1. So you can get this very nice explicit projection. So P here is a linear map. Pi is its corresponding matrix. So if I let I here represent the corresponding mixed state, you can get a couple of nice identities, and you can end up with a very nice sort of explicit equation for the dynamics of the system on T, which is a manifold with boundary. And the idea is to look at the dynamics of the system on the manifold with boundary. And the real difficulty here is the decomposition of the density operator rho into lambda and pi. And there's some sort of non-uniqueness here because of repeated eigenvalues and so on. But the nice thing is one can do this quite explicitly. And you end up
now to question time. If you want to leave 2 minutes for question. Maybe.
Yeah, no, I'm going to, so I thought I have 1 minute, right? Yeah, so I'm just basically going to stop here. So basically, I'm just going to show you a picture. So basically, you can think of it, if you like, geometry as a system divided into Weil chambers. So this is a sort of picture that looks like this, which describes those lambdas. And basically, you can think of the control problem here as driving these lambdas around on this Weil chamber. So you end up with a nice equation that's on there. And basically, the idea is lambda, which I've just described, describes the interorbit motion. And the intraorbit motion is described again by a flag, which is an orbit of the unitary group. So basically, you have this kind of nice picture, which basically just generalizes what I just described to you, where you have a control problem for the lambdas. You want to control the lambdas. Your control is over on the orbit dynamics. And again, you can get a nice equation which couples those two. And you can get nice controllability results. And it turns out that they're not exact, but you can show that at least for a large set of places you'd like to reach, you can get approximate controllability. So you can use your controls to drive you sort of within epsilon of any point that you'd like to get to in the flag, which is the analog of the Bloch sphere. Okay, so I will stop there.
Thank you very much, Anthony. Are there any questions?
I have one.
Please go ahead.
Okay, so I'm new to this, Professor. So may I just summarize very fast what I understood?
Mm-hmm.
So the thing is, you want to build some quantum devices maybe, and you have these quantum systems. But the whole issue is the quantum systems are continuously interacting with some environment.
Yeah.
So that you showed by an example where an oscillator is connected to a string, and you are saying the only effect the environment has is causing dissipation. And hence you went to Lindblad equation where there is kind of Heisenberg equation of motion with some dissipation term added to it. Am I correct up to here?
Right, you are. So of course, so in the classical setting, it's just dissipation. In the quantum setting, it can be a combination of dephasing or decoherence plus dissipation.
Plus dissipation. And then you want to control, or you want to have a control over your quantum system, which is now an open system because it is interacting with some kind of environment. Mm-hmm. And you are talking about this, how much control you have on this quantum system depends on this purity thing, and maybe I feel like you are using geometry to describe the evolution of the density matrix of the open system. I hope.
Well, that's basically right. But the purity, so basically that's right. So the idea is you'd like to control it. And so the basic idea, just going back to the two-dimensional setting, is if you don't have any dissipation or Lindblad terms, you're moving on an orbit of the quantum system, and you want to make sure that that system is controllable. So it depends on basically the structure of the Hamiltonians, but assuming that they're such that you can control it, you can move on an orbit like is the surface of the sphere and of the Bloch ball. But if you want to move in the interior of the Bloch ball, you make use of this Lindblad term. It allows you to move in the interior, and you can get certain results on controllability as well. And you can think about a completely general control problem, but one example, for example, would be to drive yourself from the interior to the surface of the sphere, which would be sort of maximizing the purity. So that's just one interesting example. We're often interested in pure states, but you can think of other sort of control problems as well.
So the Lindblad terms contains not only dissipation, but also decoherence.
Yes, absolutely.
Okay, thank you, Professor.
Maybe we can take one more question.
Yeah, maybe I can. Yeah, thank you very much for a very interesting talk. I just want to clarify, I got lost in some of the details, but the idea is that you have a Lindblad operator being given, and then you try to find the optimal Hamiltonian to control your state. Now, of course, if the Lindblad operators are given, for instance, for two-level system, if they're Hermitian, then I presume there's no Hamiltonian that will ever take you out of the origin of the
Well, no, so if the Lindblad terms are given, so without the Lindblad terms, then the Hamiltonians will keep you on a sort of orbit.
Sure.
But the Lindblad terms will sort of will remove you from that orbit in general, right? But the point is, you have control over the Hamiltonian. It's that sort of interaction between the Hamiltonian and the Lindblad piece that allows you to steer as you want, say, through the whole Bloch sphere, as opposed to just being on a particular level, if you like.
Yeah, what I'm saying is that if Lindblad operators are given, then it seems to me that there are states where you can't control. Yeah,
no, that is true. You're right. So you can't control everywhere, right? So what we do, no, you're right.
That could be fairly, I mean, it's not a very special case, is what I'm trying to say.
No,
so for example, if the Lindblad operators are all Hermitian, then R equals 0 can't be moved by any Hamiltonian.
No, that's right. So you're right. So so it is a very special case in that sense. So right. So what we do in this general setting, which I didn't have time to show here, is we can show that you can get an approximation for the regions where you can move and where you can't. So certainly that's true. And in general, of course, first of all, the Lindblad thing can be more general, and there are various generalizations. So of course, it's also possible for the Lindblad terms to vary a little bit. So they may not be. So they might be varying when you add the force. So this is an approximation, right? It's possible the Lindblad terms could change, and you can also, in some cases, you can have control over those Lindblad terms as well. So this is a very special case in some sense.
So have you thought about the opposite case where a Hamiltonian is given? And you want to add a control Hamiltonian plus a control Lindblad?
Right. Now in fact, we have thought a little bit about that. So there was some work, there's something called engineered reservoir dynamics. Lorenzo Viola looked at this. And so that's something we've been looking at as well. So so we have, in fact, we've just started thinking about that other case. I think that really is interesting, but we haven't really done the analysis for it. But it's certainly, and it's an interesting physical case, in fact.
Thank you very much.